I'm Anish, and this is my Lab 2 projectile motion for Physics 2211. So our video will go over the introduction, which is the purpose of the lab, some formulas we use, the experiment, and the data we got, our GlowScript code and our GlowScript model, the discussion of possible errors, and discussion in general, and our conclusion. So the purpose of this lab is to analyze the motion of the crumpled piece of paper, which is affected by both gravity and drag through the experimental and computational models. We will compare the observed parabolic path using tracker and then compare that path with a computational model we code from GlowScript, highlighting the force of gravity with one, and then highlighting the force of gravity with the force of drag in the other. Things we'll visit in this experiment would be the drag force, the gravitational force, and Newton's second law. So the drag force is essentially air resistance, and it opposes the motion of the ball. In this lab, we model the drag as proportional to the square of speed, pointing in the opposite direction of velocity. So our equation is F drag equals negative B times V squared times V hat. And our B is our gravitational, or our drag constant, basically. As the object moves faster, the drag gets stronger, and it reduces the speed, it reduces both horizontal and vertical speed. Gravitational force is the force of gravity, and it pulls straight downward with a constant magnitude of Fg equals vector y component is negative mg. Newton's second law says the net force of an object equals the mass times the acceleration. The object accelerates in the direction of the net force, and the acceleration gets smaller if the mass gets bigger. Some formulas we'll use is the velocity update formula, position update formula, Newton's second law, drag force, and momentum principle. So our experimental procedure is we first record the ball getting thrown up from rest and record it as it lands back on the table. We plot the center of mass in its model and model its trajectory on tracker. The mass is 0.0045 kilograms of the paper ball. Then we'll write our code in GlowScript to create a computation model. We'll create one model without drag and then with just gravity and without drag. And we'll create one model with both drag and gravity. So here's our experiment. The system is the ball of paper and the surrounding is everything else including air resistance. So here's our tracker data. Our initial position was seen here at our 0 timestamp. Our initial velocity was calculated from the first 2 timestamps. The total time it took was 7 seconds, or 0.7 seconds, and each time step is 0.033 seconds, because that's the time step of tracker. And then the mass is 0.0045 kilograms. So here's the GlowScript data. To our left, we have all the constants. Initial position and initial velocity were set to what tracker said. Our mass was set to 0.0045 kilograms. Each time step was 0.033 seconds because of tracker's frame spacing. Gravity was set to 9.8 seconds. And we had, and this is our drag variable B, we had 3 models created, one without any drag, so B equals 0, one with a drag constant of 0.002, and then one with a drag constant of 0.0001. We also created used the position and velocity update formulas here to calculate the position of the ball when drag was involved. And then here we use an if statement to get rid of the case where it reaches its maximum height and velocity equals 0, just so we don't get any errors in calculation because we just set the drag coefficient to be the vector 0, 0, 0 because there's no drag when it's at the highest point of its path. So here's the result. As you can see, here's our models with drag, and then here's the model without drag. And then here is it compared to our tracker data. The tracker data is the one with a little divot here. And as you can see, here's all 3 models on the same chart. Here's a divot of our tracker data, and here's the 2 models, one without drag, one with drag. And we decided to use 0.0001 as our drag coefficient because, as you can see, 0.002 is just too off. And here's our 2 models, one without drag, one with drag. So both computation models are slightly off from the tracker data. They don't start at the same point because of the awkward angle we had when we first launched the ball. And for us, the model without drag had a closer resemblance than the model with drag of B equals 0.0001. Some sources of error would be the non-smooth surface of the ball, human error when we plot on tracker, and then the low time interval of 0.7 seconds. So what does terminal velocity mean? The graphs don't have a non-zero slope, so the balls cannot be moving at a constant velocity. Terminal velocity happens when the net force is 0 during a fall. My velocity time graphs do not show terminal velocity because the short flight time is only 0.7 seconds, and it's not enough for the ball's velocity to level off with a small b value, especially with a small b value. A better terminal velocity experiment would be to drop this ball at a much higher height, like a stairwell, and track the y velocity until it plateaus. So what if it's thrown up at the same speed? If the ball is thrown up at the same speed, it would take more time than the original throw to reach the ground. From my experiment, the initial speed is 4.094 seconds. Throwing the ball straight up would mean that it would be introduced to the air for longer, meaning the resistance due to air would impact the time it takes to land, making it land take longer. And this is due to the equations finding when we find the time when it's thrown up in an arc compared to when it's thrown up in the air. Here it is. The sign component makes the number smaller. Thank you.